All right, so in this case, I have defined a function off to the side. I've named it franc of x, f of x. And so now I can refer to it by its name, f of x. So I just asked you two of them, the limit from the right of 0 and the limit as x goes to negative infinity. So to find the first one, the limit as x goes to 0, what method do we use for that? Direct substitution. Yeah. If we get 0 over 0, then we can divide and factor out. If we get non-zero over 0, we know it's d and e. It's some type of infinity. But I think if we plug in 0 here, we get 1 over 7, right? So that's it. That's not only the limit from the left, that's the limit from the right. That's the general limit. It's continuous there. So never not first, direct substitution, okay? The second one is the end behavior. So for the end behavior, when we have a ratio, that's when we analyze how fast the top is growing with respect to the bottom. And because we have a quotient of two polynomials, we call it a rational function. We have to look at the leading terms. Are the leading terms always in the front? No. What makes a lead dog is that it's always in the front. What makes a leading term is that it has the largest exponent. So the leading term in the top is actually in the rear, right? It's negative 7x cubed. That's the largest exponent. So negative 7 is the leading term or coefficient. And then in the bottom, we have 2x squared. So you might be kind of baited in a problem like this to say, oh, it's 4x squared over 2x squared. They grow at the same rate. It's 4 over 2, it's 2, right? But that's not right. The top grows faster. So a safe answer on a free response, would be D and E. Okay, free response. On a multiple choice, we would have to know what type of infinity it is. And again, for that, you can just plug in a representative type of number into those leading terms. So in the top, negative cubed is negative times negative 7 is positive. And in the bottom, negative squared is positive times positive 2 is positive. So a positive divided by a positive is a positive. So I don't have to adjust the infinity, right? So that would be the multiple choice. Remember, the other thing you could do is to look at the end behavior model, which I always just say y equals. If you were to simplify the leading terms, negative 7x cubed over 2, you'd get negative 7 halves x to the first, right? And then, of course, there would be like some y-intercept here, but that's not important to know the end behavior, because negative 7 halves x to the first is a line that looks like this, right? It's a negative slope. So if you want to know what the f of x is doing as we go out to the left, just look at the end behavior model, which is a line with a negative slope. So it goes up to infinity, so does f of x. Okay, cool. So be careful. I can shuffle the terms around, putting the leading term somewhere in the middle, somewhere at the back. So just, you know, always be careful. Don't step in a pothole. You do have to keep your eyes on the horizon, but you also want to watch for potholes in front of you. So true. Yeah. Okay. Any questions on that? Fun. So that is a nice segue into example 4, because if you remember yesterday, we were finding a good place for this. There we go. Yesterday, we were looking at those 3 cases when you had ratios of polynomials. And on part C, it was kind of the same idea. The end behavior limits were some type of infinity. But because the top's degree was larger by exactly 1, we know that the end behavior model ended up being linear, x to the first. And we can get the slope of that line simply by looking at the simplified quotient of the leading coefficients, which is enough to give us the end behavior. But if we're interested in like sketching it more accurately, like for local behavior, or the question asks us, what is the equation of the slant asymptote? Sometimes they're called oblique asymptotes, which just means slanted or at an angle. We need to find B. Yeah. Oh, on your desk. Okay. Thank you. All right. I will. Yeah. Okay. So while we transition to that. Oh, I know who it is. Okay. Thank you. When you're trying to find that, you just need to kind of lean into the problem a little bit harder, very attentively, okay? So I know the fan is going, but if you can kind of just be real quiet for a second and just kind of lean in, like to your iPad maybe, you know, or you can lean into the big screen. I don't know if it's any louder, but you lean in and you just kind of listen. And the problem should speak to you. I mean, some people go to the wilderness for like years to hear this, and I'm expecting y'all to hear it right away. I don't know. Like Henry David Thoreau, you know, he went to the wilderness to listen to his math problems, and he ended up writing about how to grow beans. Pretty exciting. No, I don't know if y'all heard it. I heard it, but I also know what to listen for. It's this right here. Whoa, dang. Okay, coming in a little too hot there. Yeah, he was. It's kind of a soft whisper. Oh no. It says divide me, right? You lean in and it says, divide me, please divide me. That's what that means, right? It's not just a way to write a ratio. It's an operation. It's an implied operation. So let's go ahead and indulge h of x for a second. The numerator, when you do long division of polynomials, everyone groan, goes on the inside. That's called the dividend. The numerator becomes the dividend, and the denominator goes outside and becomes the divisor. I don't know, horse and riders, you learned something back in the day, I'm not sure. Cowboy, Western, woohoo. You want to write them in descending order, okay, just so that they're all kind of in the same format. And then sometimes you write a placeholder if there's a missing term. But I don't know if you've ever done long division of polynomials. Maybe not. It's not, I mean, it doesn't really show up a lot because of, you know, COVID maybe recently. But here's what you do. To do long division of polynomials, it's not as hard as it seems. You look at the first two first, okay? And you ask yourself, how many times does negative 2x squared go into 4x cubed? Negative 2x times. Yeah. That's the same question as what is 4x cubed divided by negative 2x squared. So off to the sides on my math workbench, you could do that. That's the exact same question, right? That's a lot easier question. And what we do is we put that over the leading term in the what's going to be called the quotient. Okay, so now it's time to get the other dudes in the divisor involved. Now you multiply or distribute from up top. So negative 2x times negative 2x squared, that's going to be positive 4x cubed. At this point, those terms should be the same. If they're not, go back and do step one again, this time more correctly. Okay? Oh, thank you. Now we'll distribute the negative 2x to the next, and you get negative 10x squared. And then to the next, you get positive 18x. So we're going to do the same thing you did when you just had numbers back in the day. We have to subtract, don't we? And when we subtract multiple terms, it's, did I say? I did say, oh yeah, that plus sign. There it is, Swiss cheese brain. Here we go. Yeah, negative 2x times negative 9 is positive 18x. Very good, thank you. All right, now we have to subtract. So I'll use a different color for that. When you subtract, you change all the signs, right? All the signs change. And then you can add. That's a little bit easier. So go through and change all the signs and now add. Now you should get 0 in the first column again by design. And then what do you get in the others? You get 10 minus 2, that's 8x squared. And then 4 minus 18, you get negative 14x. And then you could bring down the negative 7. And now we do it again, okay? We repeat that process. So now you come back up to the leading terms. How many times does negative 2x squared go into 8x squared? Well, off to the side, that's the same as what's 8x squared divided by negative 2x squared. And the answer is negative 4. Negative 4. Now, at this point, if you were only looking for the equation of the slant asymptote, look what we have in the quotient. We have negative 2x, which we already knew just kind of casually by looking at the leading terms, but now we have the b, the negative 4 is the y-intercept. So you could say then that H has a slant asymptote or an SA at y equals the equation negative 2x minus 4. So why is that important? Well, if you were trying to sketch the graph, you know, you would have all of your information that we're going to be doing that in chapter 3. You gather all your information, you put your vertical asymptote possibly, you draw your slant asymptote now as a dotted line through negative 2x minus 4, and those become guidelines for the graph, okay? So right now I just might ask you what the full equation is. So the negative 2x comes like so easily, almost by casual inspection, but to get the y-intercept, you got to do a little bit of division. Now, I'm going to keep going because I want to show you why this works. Let's keep going. If I multiply now the negative 4 from up top, I get positive 8x squared minus 20x plus 36. And then, of course, I have to subtract. So I'll go through and I'll change all the signs. I get a 0, I get a 6x, and then I get a minus 43. I think. Yeah. And at this point, if you try to do the division again, it's not going to go in evenly. You're going to get like 1 over x because negative 2x squared does not go into 6x to the first. It can go into something that's the same degree, like 8x squared, or larger, but it can't go anything smaller. So when you did it back in the day, watch this. If I asked you, let's look at this off to the side. If I ask you, like, what is 43 divided by 5, right? 43 fifths, okay? That's kind of what we had up here, right? We had blah, 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 blups, right? Division. So we would come over here, 43 divided by 5, same idea. 5 goes into 4, it doesn't. 5 goes into 48 times. You multiply, you get 40. Subtract. Does 5 go into 3? No. You learn to add zeros and keep going. But at some point, or maybe initially, you like, if 5 doesn't go into 3, you stop, right? Hammer time. This is called the what? Remainder. Good. So we knew then that you can write 43 fifths can be written equivalently as 8, the quotient, Q, plus the remainder, 3, over the original divisor. Okay? And that's true. Now, at some point, your teacher told you that you could even stylistically get rid of the plus sign and call that a mixed number, right? 8 and 3 fifths. Yeah, 43 fifths is the same as 8 and 3 fifths. Well, guess what? We can do the exact same thing with rational functions. We can write h of x now as the quotient, negative 2x minus 4, plus the remainder, 6x minus 43, all over the original divisor, negative 2x squared, plus 5x minus 9. It's just another way to write h of x. Now, why did I finish that out? Well, watch this. If I take the limit as x goes to infinity of h of x, what is going to happen with this last piece right here as x goes to infinity? Or negative infinity, for that matter. It's going to get smaller and smaller, approaching 0, right? Because if I just look at that, that's x to the first over x squared. And anytime the bottom grows faster, the ratio, there you go, Angeli was honest, there you go. Anytime the bottom grows faster, the ratio goes to 0. So look at what the implications are of this. For huge values of x, approaching infinity or negative infinity, h of x, if that goes to 0, approaches negative 2x minus 4, right? In other words, h of x, which locally has all kinds of dashing characteristics, vertical asymptotes, holes, you know, local max, local mins, ooh, increasing, decreasing, turn on the catwalk. Well, for huge values of x, you miss all that, and h of x literally becomes more and more and more like negative 2x minus 4. Just like I swore it would never happen, Ethan. Here's what you have to look for. I swore when I was young I would never grow up to be like my father. But guess what? As time approaches infinity, there's little Kevin approaching Big Wayne, right? All those incidentals at the end that made me unique are approaching 0, and I am becoming my father. Okay? Dad, if you're listening. All right, anyway. All right, so that's kind of cool. You can actually see now why when we zoomed out yesterday, you know, all we saw of h of x was the line negative 2x. And now if we were to graph it, you remember we graphed it locally? I don't know if it's still up there. But if you would have put minus 4, we did say that we looked like we needed to shift it down a little bit, right? Well, now we know exactly by how much. Let's see if we could do that. It's almost too, oh, there's Mike the Headless Chicken. Yeah, he came up in another class. I don't know. Yeah, yeah. They fed him with like a dropper pipette. And he would be like, he would be trying to say, water, but he couldn't. It didn't even come out as cluck, cluck, cluck. He didn't have a head. You know, I guess enough of his brainstem was still intact that he was able to like walk around and stuff. All right. Yeah, the RAM cleared. So is it worth typing in again just to see? Yeah, okay. I mean, we are an advisor. This is character building, right? Negative 4x cubed minus 2x squared plus 4x minus 7 all over negative 2x squared. If you're doing this at your desk, you're probably ahead of me. And now I will graph negative 2x in y2, negative 2x minus 4. Okay, and if we just hit zoom 6, here comes, here, look at that funky graph. Now here comes negative 2x. Oh yeah. Oh yeah. Now it looks like it's in the right place, doesn't it? It looks like as the graph slips off the screen, it's using the line of negative 2x minus 4, as I said yesterday, the highway to hell, if you're an AC/DC fan. Or as you go out to the right, it's the stairway to heaven. Sorry, I'm an idiot. As you go out to the left, Led Zeppelin fans. And if you go out to the right, it becomes the highway to hell. Okay, AC/DC. Yeah, yeah. We could do those high fives. I'm fine with them. Yes, Mara.
So does this like graph, is it saying like it's not going to cross that?
Oh, yeah.
Okay.
It's okay to cross the slant asymptote, and a graph might, but this one does not. This one actually approaches, as h of x goes out to the left and right, it approaches the line of negative 2x minus 4 from above. Yeah. Yeah, exactly. Yeah. But we didn't even need the minus 4 to figure that out, because all we needed is to know it was a slope that had a negative slope. Yeah. So because that went down to negative infinity as you went to the right, so did h of x. So anyway, this is kind of cool how it all works together, right? Okay, cool. All right. Comments, questions on that? Sweet. All right. Well, let's jump ahead to example 5, because there's stuff on example 5 that are in the worksheet, and I know some of y'all are chomping at the bit to get that done. These are really nice types of problems because you could tie into what we just learned. We have a ratio of two functions, and it almost appears to be a polynomial over a polynomial, except there's one noticeable difference, right? There's a square root, okay? So that's interesting, because notice if I plug in a negative number, huge negative number, into the radicand, the plus 8x plus 1 is really insignificant for huge values of x. A negative number squared becomes positive. Times 9 is positive. The square root of a positive is positive. So if I plug a negative into the denominator, I'm going to get a positive number out, right? If I plug a positive number huge into the denominator, I'm going to get a positive number out. In fact, as x goes to infinity or negative infinity, the square root of 9x squared plus who cares is some positive number, right? It's always positive. But look at the top, 4x to the first. If I plug in a negative huge, it's going to be negative, right? If I plug in a positive huge, it's going to be positive. That's important because the top sign depends upon which direction you're going, but the bottom sign does not. It's always positive in this case. So here's how you do these problems. Let's look at the limit as x goes to negative infinity of f of x and the limit as x goes to positive infinity of f of x. Now, how do we contend with the square roots? Well, as I kind of already mentioned, for huge values of x again, you don't really need to worry about anything but the leading terms. Even the leading term under the radical is going to be the major contributor to the growth because the square root of the biggest number is still going to be the biggest number. Would you agree, magnitude-wise? Okay, good. So here's what you're going to do. You're going to come off to the side. I'm just going to put a squiggle. It's an approximation symbol. I call it the squiggle. This is where I come off to the side and do what I call, it's my terminology, the effective growth rate. Okay, it's going to be a 4x to the first over, what is the square root of 9x squared? 3x to the first, right? Yeah. The bottom is effectively growing like a 3x to the first, effectively. Not in actuality, but effectively. So effectively, for large values of x, this is growing like a 4x to the first over a 3x to the first. X to the first over x to the first, those are the same, right? So when the top grows at the same rate as the bottom, the limit as x goes to infinity or negative infinity, as we learned yesterday, should just be the quotient of the leading coefficients, which should be 4/3. So watch this. I did. Now, if this problem were truly, not effectively, but were truly just 4x plus blah, 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 over 3x plus blah, 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 it would be 4/3 for both the left and right limit. Here's why. Watch this. Look at the effective growth rate, 4x to the first, 3x to the first. If I plug in a positive huge x, positive to the first over positive to the first is positive, right? So I know it's going to be positive 4/3 as I go to the right. And look at the effective growth rate if I went out to the left. Plug in a negative huge. Negative to the first over negative to the first. What's a negative divided by a negative? Positive. It's going to be positive if I go out to the left as well, because they're going to divide out. But is that what's actually happening? No. The bottom is not actually a 3x to the first. So the signs are not going to divide out, giving you a positive. The top sign will continue to change depending on whether we're going to the left and right. But the bottom is eternally optimistic, right? He is always positive. Oh, yeah. So when you see the square root, it should be kind of, you know, alert, alert, alert. We have one of these eternally optimistic, cheerful, always positive things happening. So how do we know which is which? You have to get the number first, like we just did, using the effective growth rate. And then step 2, you come back and get the sign second. And how do we get the sign? Same way we've been doing. Watch. We're going to negative infinity. In the top, we can plug in a negative into the leading terms. You're going to get a negative. And in the bottom, we're plugging back into the original now. You get what? Positive. So what's a negative over a positive? A negative. Yeah. And what do you get when you plug in a positive into the actual? Positive over positive is positive. So there are your 2 end behavior limits. Does this function f have any asymptotes? Yes, it has actually how many? 2, right? F has HAs at y equals negative 4/3 and y equals positive 4/3. It kind of looks a lot like the graph of arctangent in that respect. Okay? So These guys, they should stand out to you. But what happens is we go later in the year and he shows up, you know, like around spring break, and then you forget. You forget. You look at the effective growth rate and you put positive 4/3 for both of them, and maybe you get one of them wrong. It's not always going to be opposite. It depends entirely on what the degrees are. And you could actually have like a negative number outside the radical in the bottom, which would make the bottom always negative, not always positive, right? So you just got to be careful. Yeah, does that make sense? All right, good. Go ahead then and do B on your own. Oh, by the way, the radical doesn't always have to be in the bottom. It could be in the top as well. It's kind of acting like the absolute values, if you will. Yeah, be careful when you obliterate all the stuff behind the leading terms. It's only allowed when you're approaching infinity or negative infinity. It matters everywhere else.
Can you take out the X and 3?
Mm-hmm.
I'll do that, right? Okay.
Mm-hmm.
So that's right?
That's what I would do. Mm-hmm.
Yeah, so
You get your number first, get your sign second.
how many groups?
This?
So is it just exponents you take out?
Yeah. So it's like to the 1/2 power. So it'd be like 11 to the 6 to the 1/2 power, which would 6 to the 1/2 is 3. Yeah. Yeah, the square root of anything is the same as that thing to the 1/2 power. Yeah.
Is this correct?
We're saying that that's effectively the growth rate. I'm not sure. So basically, if I just ask you to plug in like a 1 or a 2, right? You would raise it to the 6th power, but then you're going to take the square root of it. So 2 to the 6 would be like 64, but then you take the square root of it and you get 2 to the 8th, which is like 2 cubed. All right, let's see how you did, because this one has a little bit of extra trickery to it. You keep what? No, you can keep it with the radical on the bottom. That's perfectly fine. Yeah. The sign. Okay, so if you go to the left, you get the number first. If you're going to the left, just plug a negative number into here and see what sign you get. If you're going out to the right, plug a positive number in here and see what sign you get. So the fact that it's negative here, it doesn't mean it's negative here. Just like if it's positive here, it doesn't mean it's positive, okay? All right, so again, you have a quotient of 2 polynomials, but one of them has a radical, all right? When we're looking at the end behavior and the end behavior only, I always go off to the side and get the effective growth rate. The top is actually a negative 2x cubed, and the bottom is effectively whatever the square root of 11x to the 6th is. Well, if you have it under a square root, remember the square root is the same as that thing to the 1/2 power. So you just take half the largest power. Half of 6 is 3. 11 is not a perfect square, so it's just the square root of 11. So off to the side, now I can analyze the effective growth rate, and they're growing effectively at the same rate. And when that happens, the end behavior always is the quotient of the leading coefficients. Now, because there's a radical, if you notice the denominator for huge values of x, it's always going to be positive. So the fact that you get a, bless you, the fact that you get a negative here does not mean that both of these are going to be negative. Just like the fact that you got a positive over here doesn't mean both of those were positive. The number, the magnitude is what's important. Now to get the sign, you plug a representative number into the actual function, leading terms only, okay? So as I go to negative infinity in the top, negative cubed is negative. Negative times -2 is positive. And of course, the bottom is always positive. So positive over positive is positive. So now the left end behavior is +2 over the square root of 11. And by the way, you can leave it like that. You don't have to rationalize. Multiply by square root of 11 over the square root of 11. And as you go out to the right, what type of 2 over square root of 11? Well, plug in a positive. Positive cubed times negative is negative. And the bottom's always positive. Negative over positive is negative. Yep. Yep. Next. Okay. No, it would not be wrong if you rationalized it. Nope. On a free response, you don't have to rationalize. I went ahead and rationalized the second one there. If it's a multiple choice, they may rationalize, they may not. You know, if you rationalize, you just multiply by root 11 over root 11, and you get 2 root 11 over 11, okay? So again, the radical is there to warn you, to tip you off, right? To tip you off. And again, don't always just assume that if it's a radical, it's positive, because you could easily have like a negative out front or a -2 out front. If you have a -2 out front, then that becomes part of, you know, your magnitude, all right? So be careful. Okay, so y'all got one more in you here? Big K of X. All right, big K. My son, as much as he hates it, when he grows up, he's going to turn into big K. Sorry, Tate. It's just the way life works. As X goes to infinity. I don't know if women become their mother as much as men become their dads. But that's the whole basis of the, you know, progressive insurance, that guy that helps you not become your parents. That's why that's funny, right? All right, back up. Come on, you got room. You don't even know him. Come on. You know, old people. I'm only 47, but man, I feel like I'm getting there. I'm looking out the window. You're good. I trust your work. Yeah, keep going. No, man, keep going. Use your time wisely. BC best class. Right? I mean, if you were punching Landon in the back of the head, I'd probably have to ask you to stop doing that. But, yeah. Oh, there you go. There you do it when I'm not looking. You do that too many times to Landon, he gets to be my age, and he starts putting October 6th instead of September 8th on the board. Yeah, that's weird. I mean, and you were so polite, you're just like, okay, whatever. Thank you, Landon. Did you get them? Yeah, yeah, boom. Okay, so do we have HAs? Horizontal asymptotes? Uh-huh. Tired? Yeah.
Soccer ran to Rosemary.
Ooh, I used to live at the bottom. That was,
Back up it, and then ran all the way to the end of Rosemary on the other side.
the school?
Back there and
Yeah.
then came back.
Wow. Wow. I mean, you could get plenty of sleep and still do that and be tired. Yeah. So we do have the one. Yeah. All right. Cool. Yeah. Yes, 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 yes. All right. So in this one, again, you're taking the end behavior so you can look at the leading terms, which are not always in front, and the effective growth rate off to the side. Negative 5x squared over the square root of 11x to the what? Third. That's half of 6. Ah. Whoa. Those are not the same degree anymore, effectively, are they? So effectively, the denominator is still growing faster, effectively, yes? So guess what it's approaching? It's approaching 0. Yeah. Now, if you want to know from which side of 0 it's approaching, above or below, then you can plug in some numbers to get the sign. So do we have a horizontal asymptote? Yes, good. Has a horizontal asymptote at y equals 0. And it affects the graph on both sides, okay? So you could have a problem like this, and just as well, the top could have still been a larger degree than the bottom, in which case the answer still could have been positive or negative affinity. No, yeah, okay. Well, let's just talk. I don't want to write it. It's way over there. No. All right, so Mason, as we go out to the left, it approaches 0 from what, above or below? Below, good. Because when you plug in a negative number to the actual, not that one, the actual, you get a negative number. And as we go out to the right, it approaches 0 from where? Below, yeah. This one approaches from below on both sides, because now notice it's x squared in the top. So as we go out to the left and the right, it's always going to be a negative in the top. And of course, in this case, it's always a positive in the bottom. So this one does this in the end behavior, right? Approaches, right? That's good, like a pep rally dance, right? All right, everybody, stand up in the bleachers. Let's do the H of X, K of X, end behavior dance. Come on, Mason, come lead us. All right? And the crowd goes, wow. K of X. All right. Okay, so now it's time for bonus problems. Not going to be on the AP exam necessarily, but might show up, and we'll revisit this later in the year when we look at infinite series. But when you have a ratio of two functions that don't belong in the same family, like polynomial over polynomial, you can figure out the end behavior limits simply by knowing which type of member grows more quickly. So if you take computer programming in college, like there's a discrete math class you'll take, and they study how fast things grow. There's a function called the big O function, whose job it is to determine how fast things grow. Because computer programs, if they grow too quickly, they'll crash more often. So it's better to keep the number small and have it do more calculations than fewer calculations with big numbers, okay? So here is in increasing order the list of functions by how fast they grow for large values of x, magnitude-wise. Constants are the slowest growing functions. Why? Do they grow at all? No. I was born a 5. I'm going to be a 5. Sorry, Dad. Or maybe Dad was a 5 too. I don't know. Constants don't grow. The next slowest growing function, which is kind of by design, are logs. Logs are built to slow things down. Logs don't grow very fast. Now, within log functions, you have your own hierarchy. So like log base 10 grows slower than log base 5. Okay, bless you. If you think logs are built to slow things down, the bigger the base, the slower the growth. Okay, so like if you had log base 5 of something over log base 10 of something, which one grows slower? Log base 10 grows slower, so the top grows faster. That's going to go to infinity. But if they were flipped, you know, log base 10 over log base 5, now log base 5 grows faster, it's going to go to 0. You don't see those that often. The next you have is the power function. So this includes all your radicals, like x to the 1/2, and all your polynomials, like x cubed. We know how to address those, right? The larger the degree, the faster it grows. Okay, but it also works for square roots, cube roots, stuff like that. Then you have b to the x. Those are your whats? Exponentials, right? And remember, exponentials are crazy cool because they have dramatic opposite end behaviors. They go to infinity on one side and negative infinity on the other, right? But for growing, the larger the base, the faster the growth. So 3 to the x goes to infinity faster than e to the x, which is 2.718. But what that also means is that 3 to the x goes to 0 faster than e to the x goes to 0. So opposite end behaviors, right? And then you have x factorial. That's what that means, which we define that later to be, that is like a, ugh,
Yeah.
wow.
Nasty.
I don't know if it's an alligator or if it's like a Venus flytrap.
I was scribbling and I was like, that's a cool little.
That is cool. Another GT right there. We usually look at this in terms of like positive integers, okay? Like 2 factorial, 4 factorial. And this shows up a lot in probability theory and counting, because it's the number of ways to arrange X things. That's what it turns out to be. And then you have the king or queen of growth, whatever you prefer. We call this the Aleph function, x to the x. Aleph is the first letter in the Hebrew alphabet, and they're the fastest growing functions. So again, they also have their own hierarchy, x to the x versus x to the x to the x versus x to the x to the x to the x. You don't see that often. Okay, so here's the deal. If you're taking the limit as x goes to infinity of any one of these functions divided by any other one of these functions, if the function on the right is in the denominator and the function on the left is in the numerator, it's going to 0, right? And if it's reversed, it's going to some type of infinity. Okay, so we got constants, then logs, then power functions, then exponential, and that's kind of usually where it stops. But then we have factorials and the Aleph function, okay? You have Aleph naught, Aleph 1, Aleph 2, good stuff. All right, so let's try these out. The limit as x goes to infinity of x cubed over 1.01 to the x. The answer to a lot of these is either going to be like some type of infinity or 0. Yeah, 0. Okay. For small values of x, x cubed totally outpaces 1.01, except 1.01 wins in the beginning. Okay. At 0, x cubed starts at the origin. 1.01 is exponential growth. It starts at 1. So it starts off ahead, but very quickly x cubed will pass it. Very quickly. But guess what? 1.01 is like the tortoise. It's exponential growth. And eventually 1.01 will overtake x cubed. Okay, always. And that's because we're going out to the right. What would be the limit as x goes to infinity of, ooh, look at this. Pretty impressive start, right, for the numerator. 9, 9, 9, 9, 9, 9, 9, 9, 9. I'm way up here, yo. Take this, suck up. Well, the bottom is 5x minus cosine of x squared. What is cosine of x squared going to do for large values of x? X squared is going to get bigger, but that's just taking the cosine of some angle further down the line. What is cosine going to oscillate between? 1 and -1. So he's not really going to contribute to the growth. At most, he's going to be like, can I help? Can I add 1? Oh, I'm slowing you down. Sorry, I'm subtracting 1. This is dominating the growth, right? If you wanted to know what this graph looked like, you would draw the line of 5x, and then you just kind of squiggle above and below it, right? It kind of looks like a wave function going up kind of at a slope of 5. All right, so we have an x to the first power function in the bottom and a constant in the top. Who's going to win the race as we go to infinity? The bottom, and so this goes to what? 0, yeah. Now it's going to take a while for that wavy line to catch up to 9, 9, 9, 9, 9, 9, 9, 9, 9, 9, 9, 9, 9. But man, it'll pass it. Letter C, you do. Who wins? 0 or infinity? You think infinity? This is like the race of watching like a frozen sloth race like a dead snail. Yeah, like who's gonna win?
Did you see that thing where the tortoise actually beat the hare?
Oh, I did. Yeah, I saw that by design. Yeah, it's because the hair got distracted. Yeah,
It's like this little
yeah, and the tortoise was just like slow and steady. Yeah, natural log grows really, really slowly, but so does the ninth root of x. They both kind of come off concave down. But the bottom is a power function, right? X to the 1/9. And any power function will grow faster in the long run, faster than any logarithmic growth. So the bottom grows faster, so it goes to 0. Yeah. Just think logs, of all the functions that actually grow, like besides constants that we're concerned about, logs grow the slowest. Okay? A, B, C, D comes next. There's D, you do it, now do it. Ooh, 100 to the x. Man, that's fast. I wish my money grew like that. Boom. I wouldn't have to teach tomorrow, but you know what? I still would. That's right. Oh, but look at the denominator. I'm going to call it the queen of growth because, guys, you'll understand when you get older and married. Queen of growth. Right. That's why it's Queen Elizabeth, then it was just Prince Philip, you know. Who grows faster, top or bottom, for huge X? Bottom, right. So this is 0. This is 0. Boom. All right, there you go. Whoever invented cards did it wrong, right? It should be like Jack, Ace, King, and then Queen should be top card. Look at this. It's X factorial over X to the X. Who grows faster for huge X? The bottom. Does the enthusiasm of the numerator help it grow faster? Unfortunately, no. So for large X, it goes to 0. Yeah. And we're only going out to the right for these because some of these functions don't even live to the left. Are you graphing some of these? Yeah, she did? Yeah. Is it verifying our results? Oh, yes, pretty. Yeah, just like I said. Hey, how about this one? Who grows faster, top or bottom? Top. So this goes to what? Infinity. No horizontal asymptote for the first time. All right. That's a good place to stop. After lunch, we'll do example 7, okay? And then we'll be done. Have a fantastic lunch.